we got down to page, oh, I want to review this. That's right. So this says you need to know the metric prefixes. That means you have to memorize it. So let me just write out how I memorize it. And we need to know, I'll just go ahead from here, all of this stuff. Okay. So I always think of that one. And as we go larger, we go 10 to the 3rd, 10 to the 6th, 10 to the 9th, and it goes, I'll hide it. Woo! Kilo, capital M is mega, and then the biggest one is giga. Now, when I was a kid, there was nothing that was giga. It was like Back to the Future, the original movie, and he says gigawatts, and we're like, wow, that's huge. But now you've probably got like 4 gigs in your pocket. So times change. All right, now as we go smaller, we have more detail that we acknowledge because it's in the size of our hands. So we have 10 to the minus 1, 10 to the minus 2, and 10 to the minus 3. And that is deci, like dimes, centa, like centimeters or cents in a dollar. And then 10 to the minus 3 is milli. And then we get into the regular pattern, 10 to the minus 6, 10 to the minus 9. Now we're out of m's. This is micro, right? So that gets a mu. It's a Greek M. And then 10 to the minus 9 is nano. So know those conversions. One way to do that is to make a separate note sheet, like maybe even a little note sticky, or create your own note sheets where you can refer back to it, the same one that you wrote. So as you do problems, make yourself a note sheet and then use your own note sheet rather than looking it up in your materials. That helps memory. Okay, we got through these guys, and then we're introducing unit factors. And we're going to use these. There's more discussion about it for tomorrow. But this is basically something that has a number and a unit on the top and a number and a unit on the bottom, and it comes from an equivalence statement. So in A, I'm going to use this one to write something that has the format like this. So you may have that one written down, or you may be ready to go on to C. So go ahead and write that. 1 kilogram has 1,000 grams, or I could say it, 1,000 grams are in 1 kilogram. And those are equivalent. They both equal 1, which is why it's a unit factor. So doing the same thing with C, we have 1 liter has 1,000 milliliters. And notice that it's helpful in your work to remember to write it in a way that's super clear for you. And that is a small m for the milli and a capital L for the liters. Okay. Or we could say there are 1,000 milliliters in 1 liter. Sorry, that's a little sloppy. All right, we will use unit factors to make conversions. So we take a look at some of these. These are all equivalence statements. Now notice, remember that I talked briefly about how this 3 lines means is defined. Now something that is defined is exact. So that means there's no limitation on the significant figures. There are infinite significant figures. And notice that that is the case for inches to centimeters is exact. It looks like maybe it's measured, but it's actually exact. The inches arise from a Roman soldier's imperial finger knuckle. Wait, where is it? There it is. Right there, that was defined as an inch, right? So that was converted to centimeters and defined to make an exact conversion. Notice that these other ones are approximate. So this one, one other thing to notice about these is that they have to have the same number of significant figures on each side. And so in this one, I'll write it down here. I'm really saying 1 pound. And for pounds, I always write in cursive. If you use printing, it looks like 16. And then our numbers are all wrong. And I can't figure out what you did. So I always write pounds. For these ones, we won't use it much, but I always write it in cursive. Okay, 1 pound is 453.6 grams. So even though I write 1 just by itself, like this, I know because of the accuracy of the grams, I know that it's got 4 significant figures. So we'll just stick those zeros on there, or you can just remember that. They have to have the same SigFigs in the conversion. Okay, accuracy and precision. Accuracy is how close it is to the true value. And the true value, usually, this would be an average of many measurements, right? So when we talk about true value in science, we're saying that a lot of different measurements have been made, and this seems to be the right value. Everybody's close to that one. So this is usually an average over many measurements. Now, precision has to do with how repeatable it is. Okay. Well, I'm trying to be specific. How repeatable, how close they are together. So these relate to instrumentation and errors in a particular way. So we might think about a thermometer, right? Thermometer is super easy, right? We put a little bit of alcohol in a closed glass tube, and then we can put it in freezing water. We can put it in an ice bath, and that's going to tell us where the zero is. And so maybe you have a thermometer in the lab, and you put it in an ice bath, and it reads 2 degrees C. You know that the markings aren't correct. When you boil water and you put it in there, it's going to be 102. So we know that the marking is wrong. That is a systematic error. We can calibrate that. We can make sure that we adjust our scale to be correct because we know that water freezes at 0 degrees C, right? So accuracy has to do with, it tells us a little bit about systematic error. Precision is achieved, precision tells us about the random error. So let's look at these bullseyes. We're throwing darts at a target. Now, if you're really good, you can get like figure A where you get it right on the bullseye and they're all close together. I don't know, that's impossible, I can't do it. Or in part B, maybe the same dart thrower is very skilled and they're throwing the darts, but now there's a fan and the wind is blowing those darts up and over. So even though the person is throwing it really well, they're all close together, but there's a systematic error in the system. The fan is blowing the darts up each time. Does that make sense? So that shows us that there's something systematic going on. And then in the other one, well, they're more spread out. So maybe that's more like random errors, like they're outside. And sometimes the wind is from one direction, sometimes the wind is from another direction. And so no matter how they're throwing it, it gets shifted, right? So that's more of a random error. And as you take more measurements, they're going to average to one value that we end up agreeing on through many, many measurements, statistical numbers, like hundreds of measurements at least. For target A, that has lots of measurements. They're close together, and they're right on the bullseye. So it's accurate and precise. For B, they're very close together, but they're all shifted, so it's inaccurate. It's not the same. It's not the correct value. It's not the bullseye. And then on the third one, okay, this one's a little harder. These are clearly imprecise, right? They're spread out. But we have to think about where's the average. Is it accurate or inaccurate? And this one's a little hard. Let me see. When we look at these guys, those guys kind of average to about there. I don't know if you can. But then if you include that with this one, maybe it brings it's going to bring that average down and over. So maybe our new average would be like here. So I would say it's pretty accurate because the average is near the bullseye maybe. But again, we're just eyeballing it. So if you would say, oh, it's not accurate, okay, maybe that's okay too. Why is B not imprecise? Precision has to do with, are the measurements close together, right? So do they agree with one another? All right, just a little bit of vocabulary and understanding how our data connects to the way it was collected. Oh, look, you can still annotate. Nice. All right. Let's see. All right, so now we're going to get to when we look at a measurement, when we look at a device, we take a measurement, we have to write the value that reflects the instrument we used. And then if we're going to use that in a calculation, we have to propagate it through. Yeah, we have to propagate it through the calculation. Now that can get a little bit tricky because we do it different ways depending on what operation we're doing. So there's two different rules. If we're adding and subtracting, then we're going to use decimal places. So for example, if I have something like 1.2 liters, and then I want to add a microliter, or let's say 5 microliters, it doesn't make any difference in the value, right? We only know up to here. Right, we only know 1.2 liters is a lot, and a microliter is like a tiny, tiny fraction of a drop. So it's not going to really change the volume because we only measured this value to 1 decimal place. So when we add and subtract, we have to line up the decimals and use the fewest decimal places. So that one is tricky. Adding and subtracting is tricky. Whenever you're doing an operation with addition or subtraction, write that intermediate value. Write it down so that you can see the significant figures. All right, now if we're multiplying and dividing, that is the easier case, and most of our calculations involve multiplication and division. So if you're using multiplication and division, you're going to use the fewest significant figures. All right, so in this next one, the way I've set up these boxes is to identify decimal places and significant figures. So for this number here, we have 1, 2, 3, 4, 5 significant figures. And how many decimal places? 1, 2, 3, 4. So I'm identifying the decimal places and the SigFigs for every number going into the calculation. And I'm going to use that to figure out how many SigFigs or decimal places are in the answer. Okay, so this one has 2 decimal places and 3 significant figures. And this one has 3 decimal places and 5 significant figures. So how those two things relate to each other depends on the size of the number. All right, so let's calculate our answer. And I'm going to write it in the box and take a look at that. All right, so now this one, we have to decide which one we're going to use. And this has just addition. So that means we're going to decide to use decimal places. So decimal places are going to determine the decimal places of our answer. That means that how many decimal places should our answer have? We'll take the fewest. So our answer is going to have 2 decimal places. And how many significant figures? I'm going to underline that. How many significant figures does that mean are valid in this answer?
4.
4, yeah. So our answer is 26.4. And I like to do it this way.
Oh, I don't understand why it's 4.
Well, because it's addition, we're going to look at the decimal places.
After the decimal?
Yes, after the decimal.
Okay.
Right, we can always think of writing it like 7.4333 plus 8.2543. Now, we don't have the numbers here or here or here. We don't know what those are. And that means that we only know where there's numbers. So this one is good to 2 decimal places. And when we count our significant figures, that means that it's going to be 4 significant, right? The 2, 6, 4, and 6 are all significant.
So we always count the numbers after this decimal point for the SigFig for addition.
Yeah, so your answer will have the number of decimal places that match the fewest decimal places of the numbers going into the calculation. Now, I wrote this with the underline on the 6 because then I have that 4 after it that gives me any additional information. Like if I'm going to use this in a calculation again, then I would not round it. I would use the underline format. If you're presenting your results, then you will round your answer. And I like to show that with the wavy equals. And then my answer would be 26.4. Okay, does that make sense? We'll go on to the next one. All right, so same thing. We can look at the decimal places and we can identify the significant figures. And now we have to calculate our answer. Also, notice what happens with the units. They get multiplied together. So our answer is going to have centimeters cubed as the units. All right, so are we going to look at decimal places or significant figures for this question?
Significant figure.
Yeah, it's just multiplication. So we're going to look at significant figures, and we'll take the smallest number there.
Is 3.
Yeah, so this has 3 significant figures. And then we're going to use that to figure out how many decimal places. Right, so the 4, the 2, and the 9 are significant. So I'll underline the 9. And that gives me no decimal places. My answer will be presented as 429. Now, if you need to use this in a calculation, I would write it like that and rounded 429 centimeters cubed.
Can you explain a little more on how there's no decimal places after the 429.3?
Yeah, so in this one, let me rewrite it, 429.3. Because I know that my accuracy is limited by these 2 calculations here, that they have 3 significant figures. This one has to have just 3 significant figures. That means that the 4 is significant, the 2 is significant, and the 9 is significant, and the 3 is not significant. So these ones are the significant figures, and that means there's no decimal places on that value. So if we round it, we would have no decimal places showing, just the ones place. Does that help?
I'm sorry, I'm still a little confused.
Let me help you. During multiplication and division, we can see significant figures. The fewest significant figures, that means in here we have 3 numbers to be multiplied. So from that, one has 4 significant figures, but the other 2 are 3. We take 3. So when we take 3, 4 to 9 is 3 significant figures for our answer. If it is multiplication or division, we can use this rule. In case of addition and subtraction, we can see the decimal places. the fewest decimal places. And the other question on the chat was why centimeter cube? Because it is similar and multiplied. When we multiply, we can add the exponent. Each them had 1. 1 plus 1 plus 1 is going to be 3. That's why centimeter cube is. Thank you.
Yeah, so thank you, Zed. We can see we can think of it as centimeters to the 1. Does that make sense? Does that help? They just pile up.
Oh, okay. Okay, yeah, that makes sense.
Yeah, we'll look at units like if we divide, then they can cancel out just like numbers. So we'll look at that a little more. In this next one, when we add and subtract, we have to have matching units. So notice on this one, we have milliliters minus milliliters. Okay, so go ahead and fill that out if you have not yet. And our calculator says 2 points. Which one are we going to look at? Decimal places or significant figures?
Decimal places.
That's right, we're going to look at decimal places. So how many decimal places should our answer have?
2.
2. All right, we've got to add a 0. And so how many significant figures are in that answer?
3.
So we will write our answer as 2.40 milliliters. This is what I would call a measured 0. We measured the 5, and they canceled each other out, but we measured that 0. So you must show the 0. And that's why I say always write this value. So we'll look at one down here, right? So write, okay, for tomorrow's class, I want you to have a calculator that you're going to use that looks like this, not a phone calculator, not a computer calculator, a button calculator. So I want you to have that for class tomorrow, and that's what we'll do in the next section. So for now, go ahead and fill out these boxes if you haven't done it already, and we'll compare our answers. So this is the value I'm talking about here. And then on this one, that we're going to put there because we have a new calculation we'll have to look at. Okay, so give that a go before I write all the answers down. Now here the units are going to pile up again. We're going to have grams on top and centimeters cubed on the bottom. Oh, 48.6 is grams. Yes, we will distribute the units there. All right, on this one we have just multiplication and division. So we're going to use the smallest value here. 1, 2, 3. And from that, we see that we must have 4 decimal places. And if we round that, so this is our rounded answer. This one is 9.4 grams. That was my answer in the top. Let's see, this has 1 decimal, 3 sig figs. So what governs that numerator? That's just a subtraction, so it's going to be decimal places. So we'll have just 1 decimal place in that answer. And then how many significant figures does that value have? We know it's good to 1 decimal place, so that has 2 significant figures. All right, now I'm going to calculate my denominator. That one's a little bit easier to see. They all have the same decimal places and the same sig figs. And the value I get is 61.09375. And this one is multiplication division, so it's going to be governed by significant figures. So that'll have, when we look at this, we're going to be considering these guys have 2 decimal places and 3 sig figs. So we would compare 3 sig figs to 2 sig figs, so it is this one. that's going to give us 2 significant figures, 1, 2. But we cannot round it when we do our calculations. We have to use the full value or at least an extra digit. So I'm going to take my 9.4 divided by that answer.
And I have a question in terms of when you determine the number of significant figures to use in your answer. Would that be after you've simplified the problem, then before your final calculation? That's because there's two, in the way that the problem is presented, we have 3 significant figures as the lowest number. But then once you simplify it out to get the numerator and the denominator, it changes. And so now the numerator is giving us only 2 significant figures. So that's the number that we use?
Yeah, there's 2 parts of the calculation. When you calculate your value, you're going to use the full numbers, full values to calculate. Now, when you talk about the significant figures, then you're going to look at the numerator and the denominator. And that's a division. So we're going to get that from here. And we're going to get 2 significant figures in our answer. And in this case, that equals 2 decimal places. So our final answer is 0.15 grams per centimeter cubed. And that's the rounded value, because there's our full answer. Now, if you round this, if you took, let me just write 9.4 over 61. Oh, it's going to be similar, because the 61, then that is 0.154. It doesn't change our value because it's a 0. Because it's a 0 right there. But sometimes that extra digit will change our value. So you have to keep an extra digit when you calculate. You cannot use calculations with rounded values. We will end there. I will add a link, I think, to the OneNote notebook. And then you can use that in O365, and you'll be able to see the completed worksheets of what we did in class, so you can compare your answers to those. And if you have any questions about the labs or anything at all, you can always post to the forum. If you want to contact me, you can send me a message if it's private information. But if it's something about the course, you can just post in the forum. I will be looking on there.